Recently, there's been lots of really interesting methods. First one more machine learning inspired, second one really leveraging graphics, called neural radiance fields and Gaussian splatting. But actually under the hood, almost all 99% of those methods under the hood, they actually need to have the 3D position of every camera, every image before they start. And for that, they actually run Column typically and run these classical algorithms. And it's starting to change, but here's some recent work we've done in that space. Column is essentially a sequential algorithm, which brings some, makes it kind of intrinsically slow because you kind of look at all the images, you pick a good pair of images to start from, and then you keep adding locally images until you've added all the images in the collection. This is a method that's global, that essentially first assembles this full graph, and then essentially builds up, globally figures out first the relative orientation of all the images, and then figures out the position as well the feature points as well as the camera poses. And does that essentially works as well as Colmap, but typically an order of magnitude faster. And compared to, let's say, the recent deep learning-based methods that are just feed-forward, which work well on, let's say, these three types of reconstructions, typically a single object, no orbital motion around the object, or a single room, and you kind of walk around the room, and you take images, and then the network kind of figures out that, oh, this image is on the left of that image, and so on, and kind of builds up a reconstruction successfully. But none of those methods can cope with anything as you see on the down there, which these methods, the classical methods, can cope with very well, to reconstruct a whole neighborhood with many different locations that don't have any visual things in common. Which those algorithms intrinsically, by being feed forward, you have one image that's the reference. You can kind of, in one iteration, in a sense, you can only find other images that see things in common, or you can kind of guess where other things might be relative to that, but there's no way you can actually propagate, from one location to the next tree, to the next tree, to the next tree, build up a whole map. That's not possible with a feed-forward method, at least not with a limited depth in the feed-forward. Essentially, you need iterations. Of course, we also work on capturing appearances, so fitting models. So here, with known poses, so the previous method was this pixel splat method that was given two images, and the relative pose between the two images was computing then the in-between views, as you can kind of see here. So these are the two input views, first and last image from a sequence, and then this is what pixel splat does. That's the ground truth, the actual video, of which we use the first and the last frame, and then here what our multi-view splatting method is doing by actually leveraging multi-view correspondences between these. So this leverages the fact that these methods are quite good at finding correspondences. Deep learning-based methods are quite good at finding correspondence between a pair of images, even if they're quite different, and do this well. We have follow-up work that's going to be published in 2 months at CVPR, where essentially we have the multi-view branch, which makes sure that if you have two images that see the same thing, you somehow consistently reconstruct something. But then at the same time, something that's been very, very powerful recently, and that all these deep learning-based methods use, is that from a single image, you can infer lots of things about the 3D. And you've seen this all the times before, but from a single image, you can already get a pretty good idea of the 3D geometry of the scene. Okay, and so here it combines both. And so we have the multi-view consistency, we have the monocular inference kind of robustness from that. And then instead of needing 3D models to train from, because this is just about novel view synthesis, you can take any video and generate, use it as essentially supervised training data to essentially regenerate, make sure that our algorithm generates the right intermediate views that we actually have in the original video. And that way we can train our model without needing ground truth 3D data. Okay, so this is kind of how it looks like. So here you see, for example, 6 views of an apartment, and then from those 6 views, we can generate this whole tour through the apartment So you can imagine the applications in real estate, for example, that you could have with this. And so this also is a pure feed-forward system. For those methods, we still need the pole, so we've extended this a little bit further and leveraged the fact that we can find good correspondences by self-attention and cross-attention, and therefore can also implicitly learn the poles. This is very similar to what Andrea was showing, for example, earlier, but in this case focused on the task of nodal view synthesis, therefore we don't need 3D supervision to do it, we just need some intermediate images to use in the supervision mechanism. Again, here, always the first and the last image of these videos was given to the algorithm. All of the intermediate frames were generated automatically through our network. So you see we get actually quite reasonable visuals in between, including quite reasonable reflections and other kind of non-trivial visual artifacts. Okay, so then scaling this up or using these type of methods in self-driving and so on. So here, or in simulation for self-driving and so on. So here we use these methods, scale them up to larger scenes, and then have the moving parts of this also represented. This was leveraging neural radiance fields, collaboration with Meta, and then here we're using Gaussian black representations to do this. And so all the cars are actually represented separately in a kind of scene graph representation that has the scene and the dynamic objects all modeled. It's important to also take into account there the changes of appearance, due to weather, to other things, if you want to simulate this. And here's also then some nice recent work that is essentially capturing from, in this case, from a photo collection, capturing these kind of scenes, but also captures all the changes in appearance and integrate these in these novel Gaussian splatting representations. Okay, in making progress in the field, as we've heard, for example, for image recognition, we've seen ImageNet as being essentially the thing that really enabled to make a ton of progress and really enabled actually AI to kind of the deep learning methods to show something, to show their potential. Also, in all of this geometric 3D computer vision, it's important to have data sets. This is an older data set that we have developed at ETH, but it's all small scale. So it really limits ourselves to only testing algorithms that work at small scale.